Hey guys, let's go ahead and go through lesson 3, which is polynomial functions of a higher degree. Let's jump into it. It says each monomial in a sum is called a term. And terms of a polynomial written in descending order is said to be in standard form. So remember, if it's in standard form, it's in descending order. And a coefficient is the constant or the number of the value of each term. The highest degree monomial in a polynomial is called the leading term. And the constant is the number without a variable. So for example, if you have y equals 3x to the 7 plus 4x to the third minus 6x squared plus 2. Our leading term is 3x to the 7 because the degree is 7, the coefficient is 3, so the leading coefficient is 3, and the constant term is 2 because it has no variable on it. The leading coefficient test using limits. So power functions eventually rise or fall without bound as x moves towards infinity to the right or negative infinity to the left. And this behavior, we've talked about this multiple times, but we find this behavior by looking at the degree, which creates even or odd, and looking at the leading coefficient, which tells you if it's positive or negative, okay? And so we've done this before, but we know that if the coefficient sign is positive, then on the right side it goes to positive infinity, and on the left side it will go to negative infinity. If the coefficient sign is negative, then we know on the right side it will go to negative infinity, and on the left side it will go to positive infinity. If the coefficient sign is positive, then we know on the right side it goes positive, and it matches on the left if it's even, and if it's negative and even, then both sides go to negative infinity. And we talked about that in length in the first unit. Let's talk about end behavior. So we've used limit notation. They are not using limit notation anymore, but I still think using limit notation would be good for us because it helps us get ready for calculus. Consider the domain and range for each degree family. So the limit as x approaches infinity and the limit as x approaches negative infinity. What do we notice about the value of f of x or the y value of the graphs? So remember that if it's even, they have the same end behavior. And if it's odd, on odd powers, their end behavior is opposite. How does the leading coefficient a affect the values as x approaches infinity and x approaches negative infinity? That if a is less than 0, aka negative, we know that the end behavior directions change. Okay, so if we use a calculator and sketch this out, I'm going to sketch this right here. This is negative x cubed. We know that end behavior will go negative to the right, so it'll go down, positive to the left. And if I sketch this, this is some kind of what it looks like. This tells me that this n is 3 and that it's odd. So that's our how we look at that coefficient, and that our leading term is negative. So the limit as x approaches negative infinity, f of x is going to go to positive infinity, that's to the left. And the limit as x approaches infinity to the right, we know it's going to go down to negative infinity. And our turning points, meaning turning points are like, it actually looks a little bit more rounded when I graph it. Here and here are the turning points. There are 2 turning points. Let's look at the next one. So if we look here, we know that the power is 4, which is even, and the leading coefficient is here, which is positive. So because of that, we know that our end behavior on the left is going, because they're even, they're both going to be going to positive infinity. And when we look at that on the calculator, it looks something like this. So our turning points are 1, 2, 3. There are 3 turning points. Those are also called extrema. So what do we notice? That we notice that the graph has at most n, meaning the degree, minus 1 turning points. And if we look at this here, let's see, here our degree was 3, but we had 1, 2 turning points. And here our degree was 4, but we had 3 turning points. And that's because it's going to be 1 less than the number of directions that our graph goes. So we know turning points happen from when a graph goes from increasing to decreasing or vice versa. And then the second thing that we need to remember is that the function has at most n real zeros. This is our number of the degree. Okay, so let's talk about what even and odd multiplicity is. So if a polynomial function has a factor that is repeated, this is the key word in multiplicity, these duplicate roots are labeled as a multiplicity of the nth degree. If a real zero of odd multiplicity, then the graph will cross the x-axis at the 0. We'll call it c comma 0. And if the real zero has an even multiplicity, the graph will, what I like to say is bounce. Or we can say touch. Basically, it does not cross the x at the 0 value. So the way that this looks is, let's say, for example, our graph looks like this, and this value was -1. This would have an odd multiplicity at -1 because it goes through it or it crosses it. Whereas here, when we have an even multiplicity, let's say here's my graph. If my graph looked something like this, at x equals -1, I can see that it touches it and then bounces off of it, which tells me that there's an even multiplicity there. So let's look at this graph from this graphing calculator, and we can see here that this is x plus 2 to the 3rd power. So we can see the root of -2 will happen 3 times, and the root of x minus 1, that's a positive 1, will happen twice. So when I see that this is -2, that's the root that we get from here when x is -2. We can see it goes through, but that's because it has an odd multiplicity. So it happens 1, 2, 3 times, goes through, and then it comes down, and when x is 1 at its 0, it bounces off. That tells me that it has an even multiplicity at the 1 there. So here's what we know. We know x plus 2 cubed tells me that there's an odd multiplicity at the 0 at 2, 0. We also see that x minus 1 squared is the other part of that function. That's an even multiplicity, and it's at the 0 of 1 comma 0. So therefore, x equals -2 has a multiplicity of 3, and x equals positive 1 has a multiplicity of 2. So we have a multiplicity of 3 here, and we have a multiplicity of 2. So let's talk about increasing and decreasing functions. We've talked about this again in Unit 1 a little bit. Remember that a function is increasing. Whoops, we'll put that in blue. On an interval, if any values where x1 is less than x2, so let's look at that. So we already know that this is where it's increasing. So let's say, for example, if this was our value, x1, well, actually we'll call this one x1. And let's call this value x2. So as long as x1 is less than x2, where is 2 less than 6, yes, then f of x1, so this is f of x1 would be 3, and f of x2, if I look over here, is 10, that those values are less than each other, okay? So for us, that happens when x is 2, all the way, and for this one, because it goes, we have an arrow, this will say from 2 to infinity is our increasing interval. A function is decreasing on the interval, and we know that a decreasing interval is from here to here, right? Well, this is the increasing interval. The decreasing interval, so if this was, let's say this was x1, and this was x2, where -6 is less than -4, we see that here, but that their corresponding values, so f of x1 was 9 and f of x2 was 5, that the f of x1 is actually greater than f of x2. This is how we know that it's decreasing. Okay, so for us, this occurs on that entire interval from -infinity for x to when x is -3. And then a function is constant. We know where this is constant, where their f of x values are the same. And so we know that's happening here when x is from -3 to 2. Let's look at maximums and minimums. So on this graph here, we can see that we have 2 maximum values, relative maximum values, and we have 1 relative minimum value. So actually those 2 maximums are absolute because nothing goes higher than it. So we do have, it's also a relative though, because it's in this local area, it's the maximum here, and here this is also the relative maximum. So we can call this a relative maximum because it's the maximum for that specific general area around it. And then for the minimum, we can call this a relative minimum when it's the lowest point in this region. So for this example, a local max changes from increasing to decreasing. On the graph on the right side in intervals, shade it an increase of green. So I'm going to take my green highlighter and I'm going to shade the increasing intervals green, which are from -infinity until about, it's a little bit past -1, so I'm going to say to -0.8, and from +2.8 to infinity. A local minimum changes from decreasing to increasing, and we're going to shade that in yellow. And so we know that this is between, that decreasing is from when x is -0.8 to 2.8. Hopefully you can see that yellow. Okay, this next one, it says use a graphing utility, determine the relative maximum, relative minimum, and the intervals where it's increasing or decreasing. We've kind of done this before, but here's my sketch. I'm going to graph this on my graphing calculator really quick, just give an approximate. It looks something like this. It looks like a cubic function where I have 2 minimum, a local minimum and a local maximum. If I use my relative minimum function, so second trace, remember hit second trace. I think option 4 is the relative maximum, option 3 is the relative minimum. You'll look for the left bound first, so put it somewhere on the left, hit enter, find the right bound next, put the cursor somewhere on the right, hit enter, and then when it says guess, just hit enter and it'll give you these points. This tells me that we've got a minimum when x is -0.67 and y is -6.40. We have a relative maximum when x is 1.53 and y equals 38.86. Okay, so our relative max we say is a maximum value, its height is 38.86. Our relative minimum is -6.40, but it's increasing from the values of x. So remember, we're increasing if I'm looking at that highlighter, we're increasing from here to here. So when x is negative 0.67 to when x is 1.53. So let's go ahead and write that down. So from negative 0.67 to when x is 1.53. It decreases. So we're looking for these values of decreasing here and here. So here is when x is going to negative infinity. So we would say from negative infinity up until this x value of negative 0.67, and then again from when x is 1.53 all the way to when x is positive infinity. And then what's the connection to this? So the x values of the extrema, or the maximums and minimums, are where the function changes from the increase to decrease. Okay, this is the last thing we're going to go over. This is called the IVT, the intermediate value theorem. And it sounds crazy, but it's actually pretty simple. So in order to understand this, we know the theorem states that we can find two y values where the signs change, basically going from negative to positive or from positive to negative. Then a 0 has to be in between those. So let's look at a number line. So if I see that this is 0, all of these values here are positive, this is negative. So in between, going from either negative to positive, we had to cross a 0, or from positive to negative, we also have to cross a 0. So looking at this graph here, I'm going from negative values, and as we increase, we go into positive values, but in between those two values, this had to be a 0, and we see that value right here. And that makes sense. Okay, so for example, here, for example, number 5, so for example, if function g at x equals 1 equals, let's say, negative 2, and the function of g at 2 equals positive 4, even though I don't know what the graph looks like, by the intermediate value theorem, there has to equal a value where x equals some c, I don't know what it is specifically, where the function at c has to equal 0 on the interval between x is 1 to 2, since g of 1 is less than 0 or negative, and g of 2 is greater than 0 or positive. Okay. Concavity of points. A function is concave up if an open interval looks like a U or part of a smile. So we see this here, that it's concave up here, so it looks kind of like a U or part of a smile. A function is concave down and this is on an upside down U or like a frown. Okay, whoops, I was supposed to shade this in green. So concave up can be in green, sorry. Make that in green. And then a function has a point of inflection, or where these concavities change, at some value of c on an open interval if the graph changes concavity. So we can see this point of inflection is where they're changing from concave up to concave down. So here's kind of a guide to finding points of inflection. So it's where a 0 that has a multiplicity of 3. Anytime you have a multiplicity of 3, there's a point of inflection. You can estimate a point of inflection between two consecutive extreme values, so between a maximum and a minimum, or a minimum and a maximum, that it would be at where the midpoint is between those two maximum values. And then the last one is that you can estimate the possible point of inflection between a 0 with a multiplicity of 3 and the closest relative extreme value. Okay, we're going to do the rest of this in class, and I'll see you then.